Hello students, in today's session we will do a physical chemistry chapter, electrochemistry. And in electrochemistry, the focus of our discussion would be Nernst equation. Okay? Now, before we start talking about or discussing Nernst equation in detail, let's make a study of the dependence of cell potential on concentration. To understand that, let's do a quick recap of a galvanic cell. And a typical galvanic cell has been represented here, which is a Daniell cell, right? So in a Daniell cell, you have, in one half cell, you have the zinc rod dipped in or immersed in aqueous zinc sulfate solution of concentration 1 molar. Or in the other half cell, you have a copper rod dipped in aqueous copper sulfate solution of concentration 1 molar. You have the salt bridge, you've got the connecting wire, you have the voltmeter, right? And if the temperature is 25 degrees Celsius or 298 Kelvin and the pressure is 1 atmosphere or around 100 kilopascal pressure, this is under standard conditions. So we have standard conditions. So this galvanic cell has been constructed under standard conditions. Okay. So under these standard conditions, let's find out what is the E0 cell, the standard cell potential. To find out that, we need to know the individual reduction potentials. So what is the reduction potential of the zinc half cell, the zinc ion? The standard reduction potential of the zinc ion is minus 0.76 volt. The standard reduction potential of copper ion is plus 0.34 volt. Now you compare the standard reduction potentials of zinc ion and copper ion. Which has a higher reduction potential under standard conditions? Copper ion has a higher standard reduction potential. So higher drive to undergo reduction, and therefore we consider this to be the cathode. So the copper half cell will play the role of the cathode and the zinc half cell will play the role of the anode. You're all aware of this, right? So let's go back and make this let's write down this information also. The zinc half cell will now be the anode, and in a galvanic cell, the anode has a negative potential. Copper now is a cathode, and in a galvanic cell, copper has a positive potential. All right. Now let's quickly calculate E0 cell. You know how to calculate E0 cell. E0 reduction potential of the cathode. What is the cathode here? Cu2 plus / Cu minus the standard reduction potential of the anode, the zinc half cell, zinc 2 plus / zinc. So reduction potentials are used. Okay. So what is this? Plus 0.34, and this is minus 0.76, and this is plus 1.10 volt. So this is the E0 cell of a Daniell cell under, where the moment you say E0 cell, we know it is under standard conditions, right? So the cell potential, the standard cell potential of the Daniell cell is plus 1.10 volt. The concentrations of both the solutions is 1 mole per dm cubed each, or 1 molar. Now suppose, before we change the concentrations, let's write down the overall reaction. Okay, let's go to a different board. Let's write down the overall reaction. Now since the copper half cell acts as the cathode, this will be the equation Cu2 plus 2 electrons giving you copper. And since the zinc half cell acts as the anode, zinc will lose 2 electrons to give you zinc 2 plus, right? And then we cancel the 2 electrons and arrive at the redox equation, which is zinc solid plus copper 2 plus aqueous, giving copper solid plus zinc 2 plus aqueous, right? And the E naught cell is equal to plus 1.10 volt. E naught cell is equal to plus 1.10 volt. Okay, so that is what we found out now, where the concentration of the copper ion is 1 molar and that of zinc ion is also 1 molar. Now, suppose we convert this Daniell cell into a non-standard condition. Temperature is maintained a constant. Let's change the concentrations. Okay. For example, situation A, let the concentration of copper ion be 2 molar and that of zinc ion be remaining as 1 molar. So what happens when this change of concentration, or when we take two solutions of different concentrations? So in the copper half cell, the concentration of copper sulfate solution is no longer 1 molar, it is 2 molar. So look at this equation. The concentration of copper 2 plus ion is has been increased from 1 molar, correct? In this equation, under standard conditions, the concentration of copper 2 plus ion is increased from 1 molar, from the original 1 molar to 2 molar. As a result of which, what happens? The forward reaction is favored, right? Forward reaction is favored. Why is the forward reaction favored? Because when the concentration of copper ion is increased, there is a greater drive for the copper ions to pull electrons from the anode through the connecting wire to undergo reduction. And that will result in the E cell. The resulting cell potential will be greater than the E naught cell, which is plus 1.10 volt. All right. So forward reaction is favored and the cell forward reaction occurs more spontaneously and the cell potential will increase. It will be greater than the cell potential under standard conditions. Let's look at a different situation wherein we have, say B, where the concentration of copper 2 plus ion is 1 molar, but the concentration of the product zinc ion is 2 molar, or let's say 3 molar. So what has happened here? The concentration of the product has been increased. So immediately, which reaction will occur? Which reaction will be favored? Backward reaction favored. And when the backward reaction is favored, the cell reaction is opposed, right? The cell reaction is opposed. Cell reaction is what we wrote here. This is the cell reaction. The cell reaction has been opposed because the backward reaction is favored. In such a situation, when the product concentration is more than that of the reactant concentration, the resultant cell potential will be lesser than the standard cell potential, which is plus 1.10 volt. So you notice that the cell potential is dependent on the concentration of the solutions taken in the half cells in a galvanic cell, right? So now let's continue with our discussion. Okay. Before we discuss the mathematical relationship between the cell potential and the concentration of solution, let's do a quick understanding or recap of what is meant by a concentration cell. Okay, a typical concentration cell is one in which both the half cells contain the same components, but the concentrations are different. Simple example, suppose you have a silver rod in silver nitrate solution. Okay, in the right hand compartment also you have a silver rod dipped in a silver nitrate solution. A silver rod dipped in a silver nitrate aqueous solution. Okay, but the difference lies in the concentrations of both the solutions. If this is 1 molar and if this is 0.1 molar, this is a typical representation of a concentration cell. Okay, so this is what is meant by a concentration cell, where the two compartments of the anode and cathode have the same solution but of different concentrations. Now, we will not discuss the details of this. Let's now move on to what is known as Nernst equation, which signifies the mathematical relationship between cell potential, E cell, okay, cell potential under non-standard conditions. And when we say non-standard conditions, temperature is maintained a constant. It is the concentration of both the solutions in the half cells which are different. Okay, cell potential and concentration of the solutions taken in the half cells. Okay, so this is the mathematical relationship between these two quantities is what is referred to as the Nernst equation. All right. Now let's quickly understand what is Nernst equation. Let's try to understand what is Nernst equation from the free energy and concentration relationship. So this dependence of cell potential on the concentration is actually because of the dependence of free energy change on the concentration of a cell, concentration of the half cells. Now, what is this equation that relates the free energy and the concentration? This is the equation. Delta G is equal to delta G naught plus RT ln. Now, you can have a system at equilibrium. You can have a system which is not at equilibrium. If the system is at equilibrium, we write ln K, where K stands for the equilibrium constant. Now, let's focus on a non-equilibrium situation. So, K is replaced by Q. And you know what Q is? The reaction quotient. Okay? We'll soon do an example to understand that better. Now, now let's deduce an equation. Let's deduce the mathematical statement of Nernst equation from this starting equation. Now, we know that delta G is equal to minus NFE cell and delta G naught is equal to minus NFE naught cell. Now, these are the two equations under the non-standard conditions and standard conditions which relate the free energy change and the cell potential. This signifies spontaneity. That is why we know that a reaction is spontaneous when delta G or delta G naught. Let's look at the standard conditions. Delta G naught is negative, right? Delta G naught should be negative. Therefore, then the reaction is spontaneous. Now, for the delta G naught to be negative, the standard cell potential has to be positive. So, positive standard cell potential and a negative free energy change signify or result in a spontaneous reaction. Okay, so that is the relationship between the free energy change and the standard cell potential or the free energy delta G and E cell in general. So now let's substitute delta G and delta G naught in the first equation. So now we have minus NF E cell minus NF E cell is equal to minus NF E naught cell, right? Minus NF E naught cell plus RT ln Q. Let's divide the entire equation by minus NF. Divide the entire equation by minus NF. What is the outcome of that? Now you get E cell is equal to E naught cell minus RT by NF ln Q. Okay. Let's convert this to the logarithmic equation. So we get E cell is equal to E naught cell minus 2.303 RT by NF log Q, where Q is the reaction quotient. Okay, so so you know all the terms. E cell is the cell potential of under non-standard conditions. E naught cell is the standard cell potential. Now we have R, T, N, and F. What are these values? Okay, let's understand them better. So let's rewrite that equation. E cell is equal to E naught cell minus 2.303 RT by NF log Q. Okay, you know that Q is a reaction quotient. Now, we know the value of R. R is the universal gas constant, joules per Kelvin per mole. Temperature is in Kelvin scale, 298 Kelvin. This is joules per mole per Kelvin. Temperature is 298 Kelvin. F is the Faraday's constant, which is 96,000, approximately 96,500 coulombs. Okay, and what does N stand for? N stands for the number of electrons. Number of electrons transferred. Number of electrons transferred from the anode to the cathode. Okay, so those are the details of the terms in this equation. Now we can substitute these values and simplify this equation. So 2.303 RT by F is nothing but 2.303 into 8.314 into 298 divided by 96,500, and that is equal to 0.0591. So now we arrive at the Nernst equation, which is E cell is equal to E naught cell minus 0.0591 by N log Q. Okay, and what is Q? How do we represent Q? We will do an example to understand that better. Now let's do an example. So this is the equation. This is what is referred to as the Nernst equation. Okay, this is the mathematical statement relating the cell potential under non-standard conditions and concentration. Now Q is nothing but the concentration of the product divided by the concentration of the reactant under non-equilibrium conditions, when the reaction has not attained equilibrium. All right. So that is about, so the product and the ratio of the concentration of the product to that of the reactant is what is referred to as the reaction quotient. Okay, this is the reaction quotient. Okay, now let's do a problem to understand Nernst equation better. So here we have this representation. This is how we represent a reaction that occurs in a galvanic cell. From this representation, you should know how to identify which is the anode and which is the cathode. All right. So from this, you identify what is the anode and cathode. You have the galvanic cell. You can represent the anode and cathode solutions. And here we have the standard reduction potentials of the aluminum half cell and the iron half cell. If you compare these two standard reduction potential values, you can immediately identify what is the anode and what is the cathode. But let's go back to the representation and try to identify what is the anode and cathode. All right. Now, the best way to represent an anode, to represent a galvanic cell, is by this format. This is A, anode. This is the salt bridge. And this is the cathode, A, B, C. So this will constitute the anode and this is the cathode. But you notice that the concentration of aluminum rod is dipped in aluminum ion, but the concentration of aluminum ion is 0.1 molar and the concentration of the Fe2 plus ion is 0.1 molar. The concentrations of both these solutions are different, but the temperature is maintained at 25 degrees Celsius. Only then we can use the Nernst equation, right? Because we substituted 2.303 RT by F by temperature as, by taking temperature as 298 Kelvin or 25 degrees Celsius. Okay, so here this is the non-standard situation where the concentrations of the two solutions are different. Let's verify what the anode and cathode are from these standard reduction potential values. You notice that the standard reduction potential of Fe2 plus is greater than that of aluminum ions, and therefore this will be the cathode and this will be the anode. right? This is what we got from the cell representation also. So let's quickly represent the anode and cathode. So here we have an aluminum rod dipped in an aluminum ion solution. It could be an aluminum nitrate, a soluble salt of aluminum. All nitrates are soluble. Aluminum nitrate aqueous, and the concentration of this solution is 0.01 molar. Here we have an iron rod dipped in aqueous FeNO3 twice, any soluble salt, FeNO3 twice aqueous, and the concentration of this solution happens to be 0.1 molar. Okay? So now we have to calculate E cell by using the Nernst equation. So let's do the calculation. All right. The first step in the calculation is to find out E naught cell. How do you find out E naught cell? The E naught reduction potential at the cathode, which is Fe2 plus slash Fe minus the standard reduction potential of the aluminum ion, Al. This is equal to minus 0.45 minus of minus 1.66. So that is minus 0.45 plus 1.66. So that will be equal to 6 minus 5 is 1, 6 minus 4, 2, 1 point plus 1.21 volt will be the E naught cell. And the reaction is spontaneous because of the positive sign. Okay, now let's substitute this E naught cell value into the Nernst equation. Let's rewrite the formula for Nernst equation. E cell, we need to calculate E cell, right? E cell is equal to E naught cell minus 0.0591 by N log of Q. Okay, so to identify what the products and reactants are and what is the value of N, we have to arrive at the final equation, the redox equation. So which half cell played the role of cathode? The Fe2 plus. So Fe2 plus will gain 2 electrons to give you Fe, right? And on the other half cell you had aluminum ion, and aluminum is acting as the undergoing oxidation, right? There is the anode. So aluminum will lose 3 electrons to give you aluminum ion. Now we have to get the redox equation by modifying the two equations. So this is equation 1 and this is equation 2. We have to modify the two equations in such a way that the electrons get cancelled out. So we multiply the first equation by 3 and the second equation by 2, right? So what is the overall redox equation? We get 3Fe2 plus, right? The electrons get cancelled out, plus 2Al, giving you 3Fe plus 2Al3 plus. Okay, this was 3 plus. So this is the overall equation, redox equation, 3Fe2 plus 2Al giving you 3Fe plus 2Al3 plus. You can cross-check the charges. Are the charges balanced? So here you have plus 6 here and here also you have plus 6. The charges are balanced, right? Now, yes. So now let's find out. We know the concentration of Fe2 plus. The concentration of Fe2 plus is found to be 0.1 molar. And Al3 plus concentration is 0.01 molar. So Al3 plus is the product and Fe2 plus is the reactant. So what is Q equal to? The concentration of Al3 plus, you know how to write the expressions for equilibrium constant or reaction quotient, right? The stoichiometric coefficient 2 will become a power divided by the concentration of Fe2 plus to the power of 3. Okay, so what is this equal to? Concentration of Al3 plus to the power of 2. This is 10 to the power of minus 2. 0.01 is 10 to the power of minus 2 to the power of 2 divided by 0.1. 10 to the power of minus 1 to the power of 3. So what is this? 10 to the power of minus 4 divided by 10 to the power of minus 3. So this is 10 to the power of minus 1. Okay, so that is what Q is equal to, or 0.1. Now let's apply the Nernst. Let's substitute these informations that we have done found out so far, the E naught cell value and the Q value. So what is E cell equal to? E naught cell 1.21 minus 0.0591 by what is N equal to? That is an important information. 2 electrons into 3. 3 electrons into 2. So N is equal to 6. 6 will be the total number of electrons which are taken by the cathode and taken at the cathode and lost at the anode. All right. So N is 6 into log of 10 to the power of minus 1. And if you solve this, you will get the E cell value as plus 1.22 volt, 10 to the power of minus 1, plus 1.22 volt. This is E cell. And what do you notice? E cell is slightly greater than E naught cell. Why did this happen? You look at the overall equation. You notice that the reactant concentration is greater than the product concentration. So when the reactant concentration is more, then what happens? The forward reaction is favored. And when the forward reaction is favored, the cell reaction is enhanced, and therefore the cell potential will increase, right? The cell potential will be greater than the standard cell potential. So this was a discussion to make the concept of Nernst equation easy to apply in various questions that you may see in competitive exams. Thank you.